Okay, so let us proceed to another example on horizontal shear stress. So this time we're going to use the same dimension as for the first problem, but this time we're going to have W set to be equal to 200 millimeter. So in this case, our beam cross section will now be a symmetrical one. So if it is a symmetrical one, we do not need to compute for the location of the neutral axis. So the neutral axis is simply at the mid of this depth. So basically, for number 2, determine the maximum shear stress in the beam. So talking about the maximum, we are going to use the Q maximum, wherein all of the area within above the neutral axis or within below the neutral axis could be utilized in the formula tau max is equal to VQ all over IB. So first, let us have this beam cross section and set our neutral axis. Of course, neutral axis is just at the mid of the depth of this beam. Okay. See, this is our neutral axis. NE. So all in all, we have 310 millimeters. So 310 will just be divided by 2. So the location of the neutral axis is 155 millimeters from the bottom and 155 from the top as well. So with this, we can right away determine our I and Q. So this time, I'll just utilize the formula of the rectangular I if this is the centroid. See, this is B and this is the height. Okay, so it is simply BH cubed all over 12. So this is actually I bar X, or the centroidal moment of inertia for rectangular shape. So utilizing this formula, let us consider a rectangle having the whole depth and the whole height, and then we'll just have to deduct the two areas, okay, from that rectangle, okay, from the larger rectangle to the smaller rectangle. Okay, so let us deduct this one, these two rectangles from the larger rectangle. So for I bar, okay, this is just simply equal to the I of the larger rectangle. We deduct the two eyes of the smaller one. Okay, so we do not need to use the transfer formula because your neutral axis coincides with your centroid of these rectangles. So there is no transfer formula if this will be our approach. However, if our approach is to divide this again by 3 composite areas, we will need to use the transfer formula. But for our convenience, let us just apply this formula. So the eye of the larger triangle is having a base of 200 with the height of 310. Okay, so we just divide it by 12, and then we subtract, okay, these two rectangles. You can see, so the base of the each of the rectangles is 200 minus the thickness of the web, that is 175, just divided by 2. So we have 87.5 as the base of each of those smaller rectangles. And as for the height of those smaller rectangles, it is obviously 250 cube. So we divide this by 12. Okay, so we multiply that by 2 because we have two rectangles on that. So we can right away get the value of I bar x of that symmetrical cross section. So that yields to 268.65 times 10 raised to 6 millimeter raised to 4. So we are done with our centroidal moment of inertia. So this is checked, and then the width is simply equal to 25, and then we now determine the Q above or below, which is actually the Q max. So Q max will be equal to either the moment of area above or the moment of area below. So anyway, they have similar shape below and above. So from that, I'll just utilize the larger rectangle here above, okay, minus smaller rectangle, okay. So remember that Q is moment of area, meaning area times distance from the neutral axis. So doing that, say Q max is equal to the Q of the larger rectangle minus Q of the smaller one. Okay, so Q of the larger rectangle is 200 by 155. Okay, that is the area, and the distance is half of 155. Okay, 155 all over 2, and then we deduct, of course, the Q of the smaller one, that is multiplied by 2 because there are two smaller rectangles there. And as we can see, this dimension is 155 minus 30, so that is equal to 125 millimeters. And as for the base, that is simply equal to 200 minus 25, 175 divided by 2, that is 87.5 for the smaller. Okay, so by that, you can now have 87 by 125, wherein both has a distance of each centroid from the neutral axis with 125 all over 2. So therefore, our Q max is computed to be equal to 1,035,312.5 cubic millimeters. So we are now done with our calculation. We just have to substitute it in the main formula. Say our V is 30 kilonewton. So let us express that in terms of Newton. So Q is 1,035,312.5. Let us divide that by the calculated I, 268.65 times 10 raised to 6. So this is multiplied by the width, equivalent to 25 millimeters. So therefore, our maximum shear on that beam cross section is 4.62 megapascal. Okay, so that is for 7-2. So for 7-3, let's take another sheet here. So for 7-3, if the wide flange beam is subjected to a shear of 30 kilonewtons, so the same value of shear force, determine the shear force resisted by the web of the beam. Setting W is 200. So we will be using here the same beam cross section with the same computed I bar, that is equivalent to 268.65 times 10 raised to 6. So we'll just have to recompute our Q, because the main concern here is the shear at the web of the beam. So let me shade the web of the beam. Say this green portion here is the web of the beam. So actually we have two alternate solution here to come up with the shear on that portion. First, we consider a value or a range of y within the web, and by we can use or extend our y from the neutral axis up to the flange. So let us now label our location of the neutral axis. So say this is the neutral axis, and I'm gonna set a y that is within the web, because the question here is within the web of the beam. Say I'm going to construct a line here that is within the web of the beam, and then tag this as y. So we label that as y, and then all of the portion above this shall be considered as an area. So we shade that portion. Say the blue portion above that line. So we will be needing this dimension, or this excess dimension here. And remember that this dimension here is half of 250. So actually that is equal to 125 mm. So that this excess dimension here is 125 minus y. And then the shaded portion blue here, or the blue color here, will be considered in the calculation of our Q. So let us recompute for our Q. Say our Q is starting with this flange rectangle with a dimension of 200 by 30, and then the distance of this up to the neutral axis, this one, is simply equal to the total dimension here. Say this is actually the half of 310, which is equal to 155, will just less half of 30, or simply this is 155 less 15. Okay, and then of course we add this portion of the web, so plus the base is 25 by the height, which is 125 minus y. Okay, and then the distance of this centroid up to the neutral axis, say I'm gonna label that as z for a while so that we can see the calculation. So as we can see, we just consider the whole dimension 125 minus the half of this dimension, 125 minus y all over 2. So we simplify that. 125 we distribute, that is 125 all over 2, plus y over 2 is actually 0.5 of y. So simplifying it further, z, we just copy that one, and then half of 125 is 62.5 plus 0.5 of y. So finally z, we just combine that one, we have 62.5 plus 0.5 of y. So this term will now be multiplied as the distance of this web rectangle up to, for the center of this rectangle up to the neutral axis. So just copy this, 62.5 plus 0.5 of y. So calculating the first term here, we have 840,000 for the first term, and of course we intend to simplify these terms. So first we distribute this 25 on the first term, so we have 3,125 minus 25y. Then we just copy this. Okay, so we apply FOIL method to simplify this term. So we just copy that one, and then we multiply 3125 by 62.5. So we have 195,312.5. Then we also multiply negative 25y to that of 0.5 of y, and that would be equal to negative 12.5 y squared. We multiply this, negative 25y times 62.5, so it would yield to 1,562.5 of y. Finally, for the last term, we multiply 3125 by 0.5 of y. So we have 1562.5 of y. So basically, this will just be cancelled. The third term will just be cancelled. And then these two shall combine. So therefore, Q will be equal to 1,035,312.5 minus 12.5 y squared. So this shall be utilized as our Q in the formula so that we can arrive at the shear force absorbed by the web. Okay, so when we say the web, let me reiterate that you have set your y within the web from the neutral axis. And then from that, we can now utilize the formula tau is equal to VQ over IB. So when we are going to substitute that one, you can see here now that tau is equal to our V is set to be 30, okay, 30 kilonewton, or it is 30,000. And then Y here, or Q will be in terms of Y, we have 1,035,312.5 minus 12.5 y squared. So let us divide this by this constant that was computed a while ago. This one, 268.65 times 10 raised to 6 to be multiplied by for the width that is equal to 25 millimeters. So what we can do here is to combine all of this constant and then distribute it to the first and second term so that we can arrive with our tau. So we have 4.47 times 10 raised to negative 6 as the value of this constant. Then we just copy that one and then distribute. And finally, tau will be equal to 4.63 minus 5.5875 times 10 raised to negative 5 y squared. So as a result, we have an equation from tau in terms of y, because y here is changing, remember, and y covers from the neutral axis up to the portion of the web and the flange. Okay, so the next step is to integrate y here, or the tau. So remember that the root formula of tau is equal to V over A. Okay, that is the root of the tau. So therefore, we are concerned with V here, and then we are dealing with the differential area actually. Why differential area? Because the area is changing as we approach the outer portion of this lower portion and the upper portion of the web. So meaning if this is the zero line, if this is zero line, we need to integrate our y from this portion up to this portion. So meaning we'll just be integrating that one along the web only because our concern is the shear at the web. Okay, so if this is the zero line, therefore this is negative 125 and this ordinate will be positive 125. So our integrand will be from negative 125 up to positive 125. So take note of that. And then from this root formula, by cross multiplication, we can have the shear to be equal to tau times dA. Okay, so all we have to do is to integrate this to evaluate the differential area on that equation. So we do that, V is equal to integral of tau with a limit of negative 125 up to positive 125. So we just have to copy this one. Okay, we have 4.63 minus 5.5875 times 10 raised to negative 5 y squared. So evaluating our integral of a constant is 4.63 y. Okay, we use this as our limit and then minus, perhaps we can copy this. We have y cubed all over 3. So this will be integrated from negative 125 up to positive 125. Okay, so I think we have to, of course, simplify dA here. Okay, we need to express your dA in terms of y. Perhaps we can recompute this one before we are going to evaluate. dA should be parallel to what we are integrating here. So the differential area from the figure, you can see so this is the differential area, the blue portion or the portion from negative 125 up to 25. So those are the differential areas. So therefore dA is equivalent to the width 25 millimeter times the change in y. Okay, so dA is equal to 25 times dy. So let us place it in here. This is 25 times dy. So this 25 here shall be distributed to the terms inside the equation. So we just copy the integrand. So the first term becomes 115.75 minus the second term times dy. Okay, so you can now evaluate the integral. You can do it manually or could be directly solved by your calculator. Okay, so if we evaluate the integral, we'll be having a value of 27,118.65 Newton. So this is the share of the web, meaning if your beam cross section is subjected to 30 kilonewton shear force, okay, so if this is subjected to 30 kilonewton, so the share of the web, say this is the web, what is the share of the web on 30, or this is actually 30,000, is equal to 27,118.65. So this is the share of the web on 30 kilonewton. And among the rest, it will be carried by the flange. Okay, so basically, the share of the flange is 30,000 minus 27,118.65 all over 2. So they have a similar share of 1,440.68. Hence, we can see that the shear on the flange will be equal to 1,440.68 Newton. So the distribution of the shear is this. For the flange, 1,440, and for the web, 27,118.65 Newton. So all will total to 30 kilonewton or 30,000 Newton. So this is, if you're going to sum all of this and multiply this by 2, of course, will yield to 30,000. Okay. So this is the approach we're in. The solution takes off upon considering the web. Okay. Meaning my y here, or y referred from the neutral axis, will be just limited to the web. Okay, so the web itself. So I'm going to present you another solution to arrive at the same result, wherein my y here will extend to the flange. So let us do that. See, the neutral axis still exists at the mid height of this section. So this time my y will extend on the web. Okay, so this y, this is the range of my y. Unlike before, my y is within the web. So this time I'm gonna extend my y up to the flange so that the shaded portion here shall be considered for the calculation of your Q. So before we proceed with our Q, let us complete first our dimension. So the remaining dimension here is, of course, will be coming from the half of this distance. Okay. Remember that this is 310 all in all depth. Just divided by 2, we have 155 millimeters. So that this remaining dimension is 155 minus y. And then therefore, you can just revise our Q here. See, the moment of area will just be focused on the shaded portion. That is 200 by the height, which is 155 minus y, and the distance of this centroid from the neutral axis shall be considered. See, for a while again, let us denote it by z. So z is equal to 155 minus half of this dimension, 155 minus y, all over 2. So z therefore will be equal to 155 minus half of 155, that is equal to 77.5, and then plus 0.5 of y, or y over 2. Okay, that is 0.5 of y. So z finally we combine this 77.5 plus 0.5 of y. So you'll just have to copy that as the distance of your area, the shaded portion there. So we have 77.5 plus 0.5 of y. Again, we are going to expand this equation. So the first term will be 200 times 155, that is 31,000, minus 200y, and then that shall be combined to this term. Okay, so we're going to use the FOIL method. So first, we're going to multiply this. We have 2,402,500, and then this one, we have half of 200, that is negative 100y squared, and then this portion, negative 15,500 of y. Finally, both outer terms, which is 15,500 of y. So these terms shall be cancelled, and therefore Q will just be equal to this term, 2,402,500 minus 100 y squared. So again, we're going to apply the formula for tau, which is VQ all over IB. So our V is first this 30,000. Our Q is that term, 1,000 for 2,402,500 minus 100 y squared. We divided by this I, 268.65 times 10 raised to 6 multiplied by the width, and this time the width is the width of the flange, and that is equivalent to 200 millimeters. Okay, so again, we combine the constant here and then distribute on the terms inside this function. So we have 5.58 times 10 raised to negative 7. So you just have to copy this one and then again distribute this. So tau will now be equal to 1.34 minus 5.58 times 10 raised to negative 5y squared. So from this we used again the root formula. V is equal to, or tau V equal to V over A. And we are actually dealing with a differential area with the changing value of y. So therefore, V is equal to tau dA, and we integrate that one. So the shear will be equal to the integral. So let us determine our integrand here. And as we can see, the integrand will start from the ordinates of the flange. Okay, so if we're going to set this as 0, this distance is equal to half of 250, that is 125. So we will start at 125 up to this point. So we just add 125, 30. So this is 155. So our integrand is from 125 up to 155, which covered the whole boundary of your flange. Okay, so 125 up to 155. So that will be our integrand, 125 up to 155. So we just copy that, 1.34 minus 5.58 times 10 raised to negative 5 y squared, and then this is dA, and then remember to transform dA in terms of dy because we are evaluating y here. Okay, so from the figure, what is dA? dA is actually the width of the flange times dy, that is 200 times dy. So dA is equal to 200 times dy. Okay, so again we distribute 200 into the equation. Okay, we'll come up with this equation. So evaluating the integral, we will be having a value of 1452.8 Newton. So a while ago, the flange computed is this one, okay, 1440. So only a slight difference because of the rounding of the numbers. So basically, if we are going to again get the share of your web, so if this is your beam cross section, each of the flange will have a share of 1452.8, and a total of 30,000 shall be carried by this beam. Therefore, the remaining portion here is equal to 30,000 minus 2 times 1452.8, and that shall equate to 27,094.4. So therefore, the share of the web will be equal to 2794.4. So if we are going to express that in kilonewton, that is 25.09 kilonewton. So the answer a while ago, going back to the answer a while ago, we have 27.118 kilonewton. 27.118 kilonewton. So this time we came up with 27.09. So a very slight difference. Of course, because of the errors caused by the rounding of numbers. But if you're going to execute the numbers carrying all of the decimal point, it will yield the same answer. So anyway, this difference or the variance is still acceptable. So only slight difference between the two results. So at least you know how to deal with the calculation of the shear point per point or area or zone by zone. So meaning if we are concerned with the web, you can work with your y within the web, okay? Or you may work on the flange first and then just deduct the share of the flange and then come up with the share of the web in carrying the total shear force of 30,000 Newton. Of course, you can only do this if your cross section is symmetrical, okay? So but if not, you can set your y along the point of along the zone of your concern, whether it is the web or within the flange. So this is it for the problem, and please stand by for the next video. So thank you.